In this video, we're going to discuss how standing waves form in three different situations. On a string with two fixed ends, in a pipe with one side open and one side closed, and in a pipe open at both ends. We'll start with the situation where we have two fixed ends. So if I have 2 points, so we'll say this point here and this point over here, and they're separated by the distance of the string length that we're going to put between them. We'll call that L. If it's fixed at both of these points that I've drawn, both of these points are going to have to be nodes. And in between each node, there's always half a wavelength. So half of the wave is going to go in between from one node to the other. It's then going to reflect off the second node, and it's going to return to the first node. Now what we've drawn here is what's known as the first harmonic. The first harmonic is sometimes called the fundamental frequency. It is the largest wavelength and the smallest frequency that is possible to set up a standing wave in this situation. All of the other frequencies which are possible to set up standing waves in this situation are going to be integral multiples of the first harmonic. This means, for example, that if the fundamental frequency is, for example, 500 Hertz, the second harmonic will be 1000 Hertz, and the third harmonic will be 1500 Hertz. The wavelength of the first harmonic, shown here, is equal to 2 times the length of the string that's strung between the two nodes at the fixed ends. The second harmonic is the next possible frequency for us to establish a standing wave between these two fixed ends. And so the next biggest wave that I can add is if I add another node in the middle here. And so I have half a wavelength in between each node and another half a wavelength, and then it reflects back to the other fixed end. And so in this situation, the wavelength is the length of the string that stretches between the two nodes. If we add another node, we can find the third harmonic, and now the wavelength of this wave is 2/3 the length of our string. Now this pattern would continue on and on and on until we get to higher and higher and higher harmonics. And we could continue to find them through this method, but we could generalize how to find them using an equation. So we can say that the wavelength of n harmonic is equal to 2 times the length of our string, or column of air, depending on how we're doing this, divided by the harmonic number, where our harmonic is some integer, 1, 2, 3, on and on and on and on and so forth. So for example, our first harmonic up here would be n equals 1, our second harmonic down here would be n equals 2, our third harmonic would be n equals 3, and forth. We can find the frequency of our fundamental frequencies by applying our wave speed equation to the equations we've found so far. So our wave speed equation was the speed is equal to the wavelength times the frequency. We can rearrange this equation so that it's equal to wavelength and substitute it into our equations above. So for the first harmonic, we see that wavelength is equal to 2 times L, 2 times the length of our string. So this would mean that the speed of the wave divided by the frequency is equal to 2 times the length of the string also, which would mean that our velocity is going to be, our frequency, our fundamental frequency, is going to be equal to our wave speed divided by 2L. And you could do this for all the other harmonics. The next situation we're going to talk about where a standing wave is formed is when you have one open end and one closed end of a pipe. So I'll have my closed end on the left and my open end on the right. Whenever we have a closed end in a pipe, it's going to form a node. And whenever we have an open end of the pipe, we're going to find an antinode. The reason we always have a node at the closed end of the pipe is it acts like a fixed boundary. So if I have a wave and it looks something like this in my fixed pipe, when it reflects off the closed end, it's going to have a phase change of 180 degrees. This means that when it reflects off it'll be pi out of phase with the other wave that's at that point. Therefore, this point where the node is at the closed end of the pipe always results in complete destructive interference and a node. When the wave reflects off the open end of the pipe, there is no phase change, and therefore you always have an antinode, because this region always results in constructive interference between the two waves that are forming the standing wave. Therefore, when we draw the first harmonic for our open pipe, we'll start with having a node at one end and the antinode at the open end. If this pipe is length L, as we had before, that means our wavelength in this situation for the first harmonic is equal to 4 wavelengths, because at this point 1/4 of the wave takes up the entire of the pipe. An open-ended pipe is different from the closed-ended. The pipe with one end open and one end closed is different from the other simple harmonic waves you can form or in different situations, because it doesn't allow for odd-numbered harmonics. So if this is my first harmonic, the next possible harmonic is the third harmonic, where I would have a node here and I would form an antinode at the open end. In this situation, the wavelength is equal to 4/3 the length of our pipe. But our frequency, so if our frequency in this situation is F1, our frequency in this situation, F3, third harmonic, would be 3 times F1. And then because only odd-numbered harmonics are allowed, the next possible harmonic, the fifth harmonic, where we'd have a node there and an antinode at the open end. And in this situation, the wavelength of the fifth harmonic would be equal to 4/5 the length of our pipe. And our frequency for the fifth harmonic would be 5 times the first harmonic. We can generalize the equation to find the wavelength for the harmonics in a pipe with one open end by saying our wavelength to the n harmonic is equal to 4 times the length of our pipe divided by the harmonic, where n is any harmonic that's odd in this situation. So n would have to equal 1, 3, 5, so on and so forth also. The final situation we're going to discuss is a standing wave formed in a pipe that's open at both ends. So just like we had before in the pipe that was open at one end and closed at another end, whenever we have an open end, we're going to form an antinode. So if I have a pipe of length L, just like we had before, at both ends of my pipe, because they're both open, I'm always going to form an antinode. This means that my first harmonic for a pipe that's open at both ends is going to look something like this. The wavelength for our first harmonic in this situation is going to be similar to the situation where we had 2 fixed ends, where the wavelength is equal to 2 times the length of our pipe. The second harmonic we can draw, where we would have 2 antinodes at each end of the pipe, looks something like this. And the wavelength of this second harmonic is the length of the pipe. Third harmonic looks something like this, and the wavelength is 2/3 the length of the pipe. We can summarize the wavelength of the equation. We can summarize the wavelength equation for a pipe open at both ends by saying a wavelength of n harmonic is equal to 2 times the length of the pipe divided by the harmonic, where harmonics possible when the pipe is open at both ends are any integer n, 1, 2, 3, 4, 5, 6, 7, and so forth. Okay, that's all there is. Thank you.